Hey, now we're going to talk about Newton's second law. Second law is used to explain the relationship between acceleration, force, and mass. We're going to apply Newton's second law to a variety of problems. We're also going to differentiate between mass and weight, and then we're also going to talk about static and dynamic equilibrium. Now, Newton's second law simply says the acceleration of an object is in the direction and directly proportional to the net force applied and inversely proportional to the object's mass. Newton actually wrote the equation as acceleration is equal to net force divided by mass. We tend to write it as a linear equation. Force net is equal to mass times acceleration, but it's the same equation. Now, Newton's first and Newton's second law. In Newton's first law is involving inertia, rest, and constant velocity only. So the sum of the forces add up to zero. In Newton's second law, now we're talking about things that are accelerating. So the sum of the forces are equal to m times a. So if you're not accelerating, the forces add up to zero. If you are accelerating, the forces add up to m times a. Now, when we're going to apply Newton's second law, first of all, we're going to draw a free body diagram. After we draw a free body diagram, we will then draw a pseudo free body diagram so all the forces are in the direction of your axes. That will help you solve it. You don't need to draw a pseudo free body diagram until there are angles involved. Then we will write expressions for the net force in the x and the y direction. Generally, things are constrained where they can only accelerate in one direction. So that usually makes that easier. The net force in the x direction is equal to m times a in the x direction, and or the net in the y direction is equal to m times a in the y direction. And then of course we'll solve the equations. Two equations can mean you could have two unknowns. So let's look at a simple one. A force of 25 newtons east and a force of 25 newtons west act concurrently on a 5 kilogram box. What is the acceleration of the box? Concurrently simply means they're acting at the same time on the same object. So first of all, I'm going to say east is positive. When I draw my free body diagram, I have 25 to the right and 25 to the left. You could also draw on your normal force and your weight. Those balance each other out. And then I'm going to say the sum of the forces equal m times a. Well, in this case I have 25 minus 25, which is of course equal to 0. So it's not accelerating. The forces are balanced. A 0.15 kilogram baseball moving at 20 meters per second is stopped by a player in 0.10 seconds. What is the average force on the ball? Now, first of all, if we draw a free body diagram, my velocity is going to the right, but the force is being applied to the left. The ball is decelerating. It's losing velocity. So I'm going to say the sum of the forces are equal to m times a. I'm looking for the sum of the forces. But I don't know a, so I have to solve for a. A is delta v over t. Key thing to understand is always final minus initials, so it's 0 minus 20 divided by 0.10 seconds. The acceleration is negative 200 meters per second squared. Why is it negative? Because it's slowing down. So sum of the forces equal to m times a, 0.15 kilograms times negative 200 meters per second squared, negative 30 newtons. That's the force that's applied by the guy or girl that's catching the ball's hand. Now, two forces F1 and F2 are applied to a block on a frictionless horizontal surface as shown. If the acceleration is 2 meters per second squared, what is the mass of the block? Now, I'm going to say to the left is positive simply because it's going to accelerate in the direction of the unbalanced force. So I don't solve anything really to choose that. But I know 12 is bigger than 2, so it's going to accelerate to the left. Now, sum of the forces equal m times a. 12 minus 2, 12 is going in the positive direction, 2 is in the negative direction, is equal to m times a, and a is 2 meters per second squared. So therefore 10 newtons divided by 2 meters per second squared is the mass, so the mass is 5 kilograms. Next, a 25 newton force acts north and a 35 newton force acts south concurrently on a 15 kilogram object resting on a frictionless surface. What is the magnitude of A? So you have 25 minus 35 is equal to 15 kilograms times A. So A is negative 0.67 meters per second squared. We have to assume that it can push the surface down, whatever it is. Okay, mass versus weight. Mass really is a measure of the amount of inertia an object has. In other words, it's what's keeping it in place. Now, weight is the pull of gravity on that mass. And weight's going to change if g changes. So a specialized case of Newton's second law is Fg is equal to m times g, and g is 9.8 meters per second squared. Again, I'm fully comfortable if you use 10 meters per second squared. Excuse me. An astronaut weighs 1,000 newtons on Earth. How much would she weigh on planet X, where the acceleration due to gravity is 6 meters per second squared? So first of all, let's do Earth. We know the equation is Fg is equal to m times g. On Earth, 1,000 newtons is equal to mass times 10 meters per second squared. So her mass is 100 kilograms. Now, if we go to planet X, the force on X is equal to m times the g on X. Her mass doesn't change, still 100 kilograms. Her new acceleration due to gravity, though, is 6 meters per second squared, so she weighs 600 newtons. Notice how the ratio of 600 to 1,000 is the same as the ratio of 6 to 10. Now, static equilibrium occurs when there is no acceleration on an object. The net forces are balanced. Now, a couple terms that are used: resultant and equilibrant. A resultant is the result of multiple forces when you add them all together. An equilibrant is a single force vector that will bring something back into equilibrium. The equilibrant is going to equal in magnitude to the net force vector, but it's going to be opposite direction. So let's take a look at that. In the diagram, a 20 Newton force north and a 20 Newton force west act concurrently. What is the additional force needed to bring it into static equilibrium? As it stands right now, it would accelerate up and to the right. Now, remember when you add vectors that you always add them tip to tail. So I have 20 newtons plus 20 newtons. To find out the length of the resultant, I'd have to use Pythagoras' theorem. A squared plus b squared equals c squared. So it'd be 20 squared plus 20 squared is equal to the resultant squared. The equilibrant would simply be, that's your resultant. The equilibrant is simply the exact opposite of that. It's numerically the same, but it's 180 degrees out of phase. It's in the exact opposite direction. A 3 Newton force and a 4 Newton force act concurrently on an object. What force could not produce equilibrium between these two forces? In other words, what they're really asking is, what is the maximum force I could have and what is the minimum force I could have? Well, the maximum force I could have is if they're both pointing in the same direction would be 7 newtons. The minimum force I could have would be in their opposite directions, is 1 newton. So therefore I can get 1 to 7, and anything in between. I can't get 9. That's a winner. Now, dynamic equilibrium is when you have an acceleration, when you're physically acceleration. So example would be a rocket that continues firing its rockets in space. There is a net force in this case, so the object's going to accelerate. So let's look at a dynamic example. A reluctant 10 kilogram dog is being pulled by a 60 Newton force into the vet's office to get fixed. If mu is equal to 0.3 for the floor and the paw's combination, what is the dog's acceleration? It's a force problem, so we always start with a free body diagram. 60 newtons pulling the dog that way, friction's going against that, and weight and normal force cancel each other out. I'm going to say to the right is positive. Fg is equal to the normal force. The weight cancels each other out on a flat surface. It does not happen on an inclined plane. It happens on a flat surface. Excuse me. And it's equal to the weight of the dog. Well, a 10 kilogram dog would be 100 newtons. Now, the sum of the forces are equal m times a in the x direction. I'm looking for a. So I have 60 newtons minus the force of friction equals m times a. Now I must know the force of friction because I'm looking for A. Force of friction is mu times the normal force, 0.3 times 100. So 60 minus 0.3 times 100 is equal to 10 kilograms times A. 60 minus 30 is 30. 30 divided by 10 is 3 meters per second squared. I hope this helped.